Good afternoon. Welcome to Lesson 4. This is it. We're in the home stretch. We only have a couple more lectures to go, one more section of tests and exercises to do, and the class is all done. So congratulations for making it this far. Tonight we're going to start in with Chapter 10, and what we're going to cover tonight are network theorems, just like it says right up here. Network theorems, and we're going to cover the superposition theorem, Thevenin's theorem, and we're going to talk quite a bit about Thevenin's theorem, and then we're going to look at Norton's theorem. And that's about all we're going to have time for before my voice goes out tonight. Next week we'll continue on, we'll finish out Chapter 10, and we'll actually do what little we're going to do in Chapter 11 and Chapter 12. Because Chapter 11 and Chapter 12 are just pretty much a cakewalk once you finish up through this. So you can pretty much guarantee there's only about 2 lectures left, and then it's up to you guys to ask questions before the final. So, with that said, let's go ahead and get straight on into it. And, whoops. Here we go, network theorems. We're trying to get this thing to go here, and it's not wanting to go. So let's try it this way, shall we? There we go. Alright, so the first theorem we're going to cover is the superposition theorem. And what the superposition theorem does, it extends the use, just like it says, extends the use of Ohm's law to circuits with multiple sources. That means we've got more than one voltage source. However, there are a few conditions that have to be met. Okay, the first, all components must be linear, which means that the current is proportional to the applied voltage, i.e. resistors. And then, oops, I guess I went twice. There we go. All components must be bilateral, which means it doesn't matter which direction current is flowing, you're going to get the same result. Now you can use some passive components, okay? Now resistors, that's pretty much what we've been talking about the whole time up to now. So resistors, capacitors, inductors, they don't amplify for the most part, especially with capacitors. The most part applies to the capacitors. It doesn't matter what direction you put them in. Of course, there are capacitors that have direction, they have polarity, but not all. You can use those kind of items. They don't amplify or rectify anything in any way. However, you cannot use active components. Okay, no semiconductors. You can't use transistors, semiconductors, diodes, tubes, because those components have one direction only generally, and they are rarely, if ever, linear. So you can't use anything else. And in our case, all we're using is resistors, so we'll just continue on. Okay, so in a linear bilateral network that has more than one source, the current or voltage in any part of the network can be found by adding algebraically the effect of each source separately. Alright, what that means is we just short out the other source and act as if there's only one source, and we check both sides. So now this kind of analysis we're going to do either by shorting the voltage source, which we're generally going to do, or if we considered a current source, we would open the current source. We wouldn't allow it to have any direction. Okay, so what they're talking about here is we have a network with 2 sources, a -9 volt source and a +24 volt source. Now what we're going to do is we're going to analyze this circuit, and we are interested in what's going on at point P here. So we're interested in one source at a time. So essentially we're going to take, at one point we're just going to short across there, and at the next point we're going to short across there. Or in this case, we've just shorted across the minus 9 volts, so that's minus 9 volts shorted. So basically point B is going directly to ground. And then we check out the voltage available at point P. Now, as you see, point P is measuring from this point to ground, or essentially across the 60k ohm resistor. So, what's the voltage at the 60k ohm resistor? Well, we know this from our voltage divider method. We've got a total of 90k, 30k ohms plus 60k ohms. So that's 24 volts times 60k over 90k, or 24 times 2/3, and 2/3 of 24 happens to be 16 volts. So then we come over here and do the same thing to the other side. We short across the plus 24 and allow the minus 9. We're going to analyze using minus 9 volts. So in this case, we're going to be measuring across the 30k ohm. That's what point P to ground is going to show us. So we've got 30k over 90k times 24, or 1/3, pardon me, 30k over 90k, looks like 1/3 to me. Yeah, there he is. $30,000 divided by 90,000 equals 1/3. That's what I thought. Times 24. It equals 8 volts. Well, that's not right. Let's see where oh, I see where I did wrong. See, I was thinking 24 volts when it's actually minus 9 volts. So in this case, over here, it's minus 9 times 30k over 60k, or 1/3. And 1/3 of minus 9 is minus 3, and there we go there. Minus 3 volts. Now we just add these guys together. Plus 16 plus a minus 3, I'm going to end up with 13 volts at point P, just like that, with both sources going on together. So that's a brief look at superposition. Let's go and do a little bit more with it. Alright, we're able to do the same thing with a series parallel with two different voltage sources. Alright, in this case we're going to, there we go, short across the 13 volt side. So now we're looking at 15 volts, and I've got, of course, a parallel circuit of R2 and R3 in series with R1. And if we look at the let's see here. Yeah, if we look at the equivalent resistance of that parallel circuit, alright, so now I'm going to need my calculator back up here. So I got 10 ohms plus 20 ohms, and of course I'm going 1 over x because I'm taking the conductance of the two, adding the conductance, Taking 1 over, and our equivalent resistance is 6.67. And then, of course, I'm in series with a 100 ohm resistor. And let me get that out of the way and go back to the drawing board here. So this equivalent resistance here is 6.67 ohms in series with a 100 ohm resistor. So my equivalent resistance, I should be working down here actually. My equivalent resistance is 106.67. Of course, they say 106.7 because they round up a little bit more than I do. So 106.67 equivalent resistance with a 15 volt source. If we do the math, what we're going to find is our total current is 1.41 amps. See, we can analyze this going with current. So we can find out what the current is going through R3 with 2 sources at this point. So where was I? Okay, 1.41 amps. Pardon me, 0.141 amps. And the current flowing through R3 is going to be 0.094 or 94 milliamps. Now, of course, we figure that out by taking we're using the conductance method. So using the conductance method, I can say 10 1 over x divided by 6.67 1 over x equals 0.667 times the total current, so my current going through my 10 ohm resistor then is 94 milliamps being fed by the 15 volt source. Now we got to come over and do the exact same thing with the 13 volt source. So now we short out the 15 volt source. There we go. And repeat using the 13 volt source. Well, this time I've got a 100 ohm and 10 ohm resistor in parallel in series with the 20 ohm resistor. So we go through the same thing. We figure out what the equivalent resistance is, calculate our current. Now in this case, our equivalent resistance is going to be 29.09 because we'll find that 9.09 ohms is the equivalent resistance of the parallel network plus 20 ohms. 29.09 ohms, which means our current is going to be 447 milliamps. And doing the conductance method once again, we find out that the current flowing through the 10 ohm resistor at this point is 406 milliamps. So that's the current flowing this direction. Now you see that the current is flowing in the same direction between the 2 sources, which means we get to add that current up once again, and the current flowing through our 10 ohm resistor is 500 milliamps, or half an amp. And that's what the next slide is going to show us. And there we go. So 10 ohms at 500 milliamps. That means we're going to get 5 volts of voltage flowing through that resistor, with using both power supplies at the same time. Okay, that's superposition. Just doing the math, one voltage source at a time. Okay. All right, now using Kirchhoff's voltage law, and this is something that would have been more in tune with Chapter 9, but we don't do Chapter 9 in this class. But what we find out is we pretty much are working in kind of a closed loop here. So if we have 5 volts at 5 volts? Yes, 5 volts. 5 volts, 10 ohms. R1 has got to be using up the rest of the 15 volt source. And R2 has got to be using up the rest of the 13 volt source. And pardon me, and there we go. And that's how you figure out all the voltage drops in the rest of the circuit. It's pretty much as simple as that. Okay, that was superposition in a nutshell. Now, we're going to be making use of it more in conjunction with some of these other theorems, but that's your first snapshot of it. It basically says we're able to take one voltage source at a time to come up with the calculations for the entire circuit as a whole. Now, Thevenin's theorem simplifies, as it says here, it simplifies the process of solving the unknown values of voltage and current in a network by reducing the network to an equivalent series circuit. Basically, it's going to allow us to create a voltage divider that we can then vary the load on and easily analyze the effects of the load, as opposed to having to do a full set of calculations every time we change the load. So we can do one set of calculations and then apply those to different loads. So what it says that any network with 2 open terminals can be replaced by a single voltage source, the Thevenin equivalent, and a series resistance, the Thevenin equivalent resistance, connected to the open terminals. A component can be removed, read load. You can remove the load from a loaded voltage divider and create your Thevenin equivalent circuit. So here we have a loaded voltage divider. Don't let it throw you by the fact that they've just flattened out the first resistor. So your voltage divider R1, R2 is then loaded by your load. Well, the first thing we're going to do is we're going to remove the load to produce 2 open terminals. And then we're going to look at the voltage across those 2 terminals. So in this case, we've got a voltage source of 36 volts. We got a voltage divider of a 3 ohm and a 6 ohm resistor. Well, just by observation, you can see the 6 ohms will take up 2/3 of the total resistance. So 2/3 times 36 volts, you'll find the voltage of points A and B equals 24 volts. So your Thevenin equivalent voltage is 24 volts. Because you're just looking at the voltage at the open terminals you made by removing the load. And then what you do is you short across your voltage source, and once again you're going to look back from your load point. and you're going to look at that circuit. Well, if you look closely and you were to apply current, you would find current at point A has two different branches. So now, looking in from point A and B, you have a parallel circuit consisting of a 3 ohm and a 6 ohm resistor. Do the math to get the equivalent. You'll find that your Thevenin equivalent resistor equals 2 ohms. So that's what you would see measuring back. If you were to stick an ohm meter out here, you would see a Thevenin equivalent of 2 ohms. So now you can redraw your voltage divider as a Thevenin circuit. A single voltage source of 24 volts and a single series resistor of 2 ohms. Now you just stuff your load in there and calculate what the effect of the load's going to be. So in this case, you have 24 volts, you have 2 ohms and 2 ohms, so you know your voltage at your load is going to be 12 volts, which means you're also going to be 12 volts divided by 2 ohms is going to be 6 amps. So it made it quite a bit easier now. I can throw in any load here and quickly and easily calculate what my drop across that load is going to be by having first set up my Thevenin circuit. So let's do that one more time. I'm going to go backwards. Alright, so now I'm not having to figure out an equivalent resistance there. I get my voltage by removing the load and measuring what my load would be, or what my voltage would be across that load, which means across a 6 ohm resistor. So once again, 6 ohms over 9 ohms, that is 2/3 times 36. I get 24 volts for my Thevenin voltage. I then short across the voltage source and look at the resistance from terminals A and B. Looking at the resistance, I can see that I've got a 3 ohm in parallel with my 6 ohm. So that circuit is going to form a 2 ohm resistor. Now I'm ready to set up the circuit, and at no time do I have to go back and repeat over and over and over again the calculations of the equivalent resistance, current, voltage. Now that I've got this circuit set up, I can just stuff my resistor in and treat it like it's a 2 resistor, my load in and treat it like a 2 resistor series circuit. And it doesn't matter what value of load I put in, I can easily calculate my load voltage and my load current. Alright, and here we have the same instructions I just gave you. Alright, in a case of I've got multiple resistors here. Alright, I've got a different type of series parallel circuit, but this is still my load out here. Well, I'm going to pull that load out once again and look back from points A and B. So if I'm looking at the voltage without this in there, as a matter of fact, let me erase that. Okay, looking back at the voltage, or the voltage from points A and B, I'm still measuring effectively across R2. This resistor, the 4 ohm, is open. It has no current path. Therefore, I'm going to see the potential across the 6 ohm resistor again. So my voltage still remains that 24 volts because I'm still at a 36 volt source. I still have a 3 ohm and a 6 ohm. That math doesn't change. That's 24 volts. Until I short across my voltage source and look back from points A and B. Now, using an ohm meter, that 4 ohm becomes part of the circuit again. So I still have 2 ohms here in series with a 4 ohm, so my Thevenin equivalent then has a 6 ohm resistance. R3 makes absolutely no difference at all when measuring voltage, but it does make a difference when it comes to looking at resistance. And once again, we can throw that 2 ohm resistor back in here, and we'll find that it is approximately 1/4. In this case, it's 1/4 of the total resistance. So 24 divided by 4, 6 volts, 12 amps. Okay, now we're back to the circuit that we had earlier with 2 voltage sources. In this case, they've changed the values a bit. 2 voltage sources, and our load resistor is right here at R3. There's our RL. And we're still looking from points A and B. In this case, we are going to Thevenize this circuit, and we're going to use the superposition theorem at the same time. So to find our Thevenin equivalent voltage, we're going to take it one source at a time. So going to jumper across there, and we're looking at points A and B with 84 volts. Well, if I look at point A and point B, I see my current coming this way. So I've got my plus lead here, and the current's going to come this way. I've got my negative lead there, and what we're going to find is we're actually measuring across the opposite side resistor. Alright, so we're measuring from here to here, which gives us the voltage drop there. So we're looking at approximately 1/5 the total resistance, with 84 volts as my voltage source. So 84 divided by 5 is going to equal 16.8 volts. And because it's a negative source, I'm going to see negative 16.8 volts. If I then short out that side and use my 21 volt source, I've got 12 ohms over 15 ohms, which is what's that, 4/5? 12 over 15, yeah, 4/5. So I'm looking at 4/5 of 21 volts, which is about 16.8 volts. And once again, current's going the same way, and I get to add these up my Thevenin equivalent voltage is 34.6 volts, or pardon me, 33.6 volts, which actually it says so right there. So that's how we get our Thevenin equivalent with multiple sources. Then once again, we're going to short across both power supplies and look at the resistance from points A and B. Well, that basically puts a 12 ohm and a 3 ohm in parallel. And if you do the math, you'll find that your Thevenin equivalent resistance is 2.4 ohms. So here's your Thevenized circuit. You can put the load back in, which originally was a 6 ohm resistor. So 2.4 ohms and 6 ohms. So 8.4 ohms with 33.6 volts. It says it's 4 amps, but I'm going to do the math anyway. Six divided by 8.4 equals 0.71428 blah 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 blah. Times 33.6 equals, well, 24 volts. So there's going to be a 24 volt drop there, and 24 divided by 6 gives us 4 amps. So that, all those numbers are absolutely correct. So that's taking this circuit and we reduced it down to this right here. It's a lot easier to analyze this than at a glance than it is to analyze this just all by itself. Oh, but wait, there's more. We come back to our old friend, the Wheatstone Bridge. Well, the Wheatstone Bridge, if we look closely, is nothing more than two parallel series branches joined in the middle, in this case, by a 2 ohm resistor. If we redraw it, oh, come on, there we go. We find that it'll look something like that. So let's Thevenize it. And when we Thevenize, of course, we're removing the load. So we remove the 2 ohm load, and now we're looking back at the circuit from points A and B. So if we look at from points A and B, we know that I've got 30 volts across this branch, and I got 30 volts across this branch. So point A to point B is either looking through there, pardon me, or looking across there. So on this side, my 30 volts is going to be broken up into 20 volts and 10 volts. On this side, it's going to be looking at 12 volts and 8 volts, because once again, series, 2 resistors, each one's got its own voltage drop. So from point A and B, I've got 20 volts and a minus 12 volts. Pardon me, minus 20 volts, because, all right, we've got to look at, there's the minus side, there's the plus side, there's the minus side, there's the plus side. We're looking at a negative supply here, which is why the negative side is on top. So while the absolute voltage drop is minus 20, and the absolute voltage drop is 12, we got to add the sign. So minus, minus, and in this case, when we're Thevenizing a bridge, we're actually subtracting the two sides. So minus 20 minus a negative 12, we get minus 8 volts. So there's our Thevenin equivalent voltage is minus 8 volts. Now we short across this guy, and once again look back from point A to point B. Now this is one of those that I find it most convenient to redraw it. And I'll start at A. Okay, A goes out, and I've got two resistors joined on the back side. There's point A. I've got two resistors joined on the back side, plus they're joined on the front side also. And they're going, and then over here we're joined there, and we are joined here, point B. So that path there back into B. So I have two parallel networks in series from point A to B, and that's what they've drawn here, just in a different way. But for my mind, I find it easier to go from left to right and straight across from point A to point B. So then I just look at my values here. One parallel has 3 ohms and 6 ohms. Well, we already know that's a 2 ohm network. The other side is 4 ohms and 6 ohms. If we do the math for that, we'll find we've got 2.4 ohms. And because they are in series, 2 ohms, 2.4 ohms, you see that they are in series from point A to point B. So 4.4 ohms is my Thevenin equivalent resistance. And so that whole circuit ends up with my Thevenin equivalent resistance, my voltage 8 volts, drawn so it is in the negative configuration. So 2 ohms and 4.4 ohms. The effect my load will have is it will draw two divided by 6.4 equals times 8 equals 2.5 volts. And somehow I lost my that's going to have that cut down there. 2.5 volts divided by 2 ohms equals 1.25 amps, just like it says in the fine print there. 2.5 volts, 1.25 amps. So we've taken a bridge circuit and we've reduced our analysis to this. Now our bridge circuit didn't change, so that's going to remain the same. It's going to be the value of our load. We can throw in any load and quickly analyze what the effect's going to be. So that's what Thevenizing does for us. Now, much like Thevenization, we have Norton's theorem. Now, Norton's theorem, instead of using voltage sources, we use current sources. And we can analyze the same kind of circuit, only instead of reducing it to a single series resistor in line with a voltage source, we're going to create a current source with a parallel network. So, we are going to simplify networks in terms of currents instead of voltage. It reduces a network to a simple parallel circuit with a current source. Norton's theorem states that any network with two terminals can be replaced by a single current source and a parallel resistance connected across the terminals. And of course, those two terminals are usually labeled something such as A and B. That's where your load used to be. The Norton current is usually labeled Norton equivalent current or Norton equivalent resistance. So a current source. We're used to seeing voltage sources drawn as batteries. That's what we've been using mostly in this class so far. You can also get a voltage source that looks like that, or it may look like that, indicating an AC source. A current source will be a circle with a line for the direction of current and an arrow for the direction of current. So we would know that that's the negative terminal because current's going to go that direction, and this would be the positive terminal because current's going to come back. So now we have a basic circuit. Okay, a series resistor with some load. We can create the terminals A and B once again by removing the load. And what that's going to do, it's going to put our resistance in parallel with the current source, and then we can eventually put our load back in. And of course we can figure out the current by using conductance, the conductance method, to figure out the total current flowing through each branch. Okay, we recovered from that. Alright, let's see about getting us to where we need to be. Here we go. Alright, so the first thing we're going to do to let's see here. We got that, I got that, I got that. Alright. Current source, determine a short circuit. Alright. So what we're going to do is first we're going to come up with the current value. What value is our current source going to be? Well, to do that, at points A and B, or across our load, instead of pulling the load out to start, we're going to short across it. And then we're going to analyze the circuit from there. So in this case, I've shorted across, so basically I've eliminated the 6 ohm and the 2 ohm, leaving me with a resistor of 3 ohms and a voltage source of 36 volts. Well, 36 divided by 3 we're going to end up with 12 amps. So our current source is going to equal 12 amps. Now we're going to pull that short circuit away and pull our load away and short across our voltage source. And once again, look at the value of the circuit back from points A and B. Well, in case you don't recognize this circuit, 3 ohm, 6 ohm, we're going to have an equivalent resistance of 2 ohms. And watch and see if I'm not right. Whoops. Okay, so we did the jump across, 36 volts, 3 amps. There are 3 ohms. We ended up with a Norton equivalent current of 12 amps. Then we pull our resistor out, our 2 ohms, and look back at the circuit from points A and B, and our equivalent resistance at that point is 2 ohms. How about that? Just like I said there would. So now what our circuit is going to look like for analysis, we're going to have a current source, two ohm resistor, and then our load, which in this case is 2 ohms. Well, I've got 2 identical branches here. I've got 12 amps, so I'm going to get 6 amps going up each of these. So our load of 2 ohms is going to give me 6 amps. And of course, we could run the conductance method and come up with the current going through each branch. For the sake of time right now, I'm not going to do that because I've demonstrated that a number of times now. But just like I was telling you, this is what we come up with. We Nortonized the same circuit that we Thevenized before, and we came up current going through our load, 2 ohms. 2 ohms times 6 amps, 12 volts. And if you'll recall back, you'll find that we had the exact same result when we Thevenized the circuit. Okay, so Thevenin's theorem says that any network can be represented by a voltage source and a series resistance. Norton's theorem says the same network can be represented by a current source and a shunt resistance. So we can convert directly from one form to another. And yes, it can be useful depending on the circuit. Okay, a Thevenin equivalent of a 15 volt source, there we go, 15 volt source and a 3 ohm resistor. Well, 15 volts divided by 3 ohms is 5 amps. So the equivalent circuit would be a 5 amp current source with a 3 ohm shunt ready to plug in whatever you need for a load. You see they are directly convertible there. Okay, in this case 36 volts. We ended up with the equivalent of 24 volts and 2 ohms. Our Norton equivalent was 12 amp and 2 ohm shunt. Okay, converting voltage and current sources can simplify circuits, especially those with multiple sources. Okay, remember this guy with the 84 volts and the 21 volts. Now we went through the circuit where we used the superposition theorem, and then you converted that to the Thevenin equivalent. Well, we can easily then just look at it this way. We pull the load and we look at one side at a time. Just like Kirchhoff's current law says we can do this back in chapter 9, which we didn't cover. But we can analyze this by looking at 84 volts and 12 ohms, which is 7 amps. 21 volts and 3 ohms, that's 7 amps. We can then state this equation with two shunts, a 12 ohm shunt and a 3 ohm shunt, two 7 amp sources, and since the current is going the same direction, we end up with a 14 amp current source and a parallel of a 3 ohm and a 12 ohm, which you will find turns into a 2.4 ohm equivalent, with our 6 ohm load. So instead of going through everything we went through using superposition and the Thevenin formulas, the Norton equation makes this one much simpler. So instead of using a voltage source, we just run it straight across with a current source. Okay, in this case, we basically have two series current sources with a load out here. Not quite as easy to analyze this, but if we switch it to a voltage source conversion, we can look at 4 ohms and 2 amps. Our voltage source is 8 volts. 2 ohms and 5 amps. We've got a voltage source of 10 volts. Our shunt resistor is now a series resistor of 2 ohms. Our other shunt resistor is a 4 ohm. And then our equivalent circuit is 18 volts and a 6 ohm series resistor with our load. So this is a case where it is beneficial to convert from current source to voltage source and then do our circuit analysis. Let's see here. Don't know if I'm ready to do Millman's yet. Let's see, it is that time. My voice is starting to go. Well, let's quickly touch on Millman's theorem. Okay, so far we've been looking at all these circuits with a load and different voltage sources. Well, Mr. Millman came up with a shortcut for parallel networks with multiple voltage sources. So we are able to find the common voltage across any number of parallel branches with different source voltages. And what it states is, for the voltage across any 2 points, we can look at the current, the sum of the currents of each branch. Okay, V1 over R1, that should give me I1, right? I2 and I3, etc. So the current for each branch, the sum of the current of each branch over the sum of the conductances, or the total conductance for each branch. And basically what this formula is doing is converting the voltage sources to current sources and combining the results. And let's see if we got an example here. Here we go. Here we have that exact same circuit that we played with in Thevenin and Norton. Now we're going to convert it using Millman's theorem. What Millman's theorem says is the sum of each branch's current, taking each branch by itself, over the conductance of each branch. The sum of the conductances of each branch will give us the common voltage across any 2 points, that is, across our load. So in this case, I've got minus 84. Remember, if the negative node is at the top, it's a negative voltage. So minus 84 over 12 plus 0 over 6. There's no voltage, so 0 divided by 6 plus a minus 21 over 3 over 1 over 12, because there's our 12 ohm, plus 1 over 6 plus 1 over 3. Now, instead of doing fractional notation there, I'm going to bring up my calculator. So let's bring the calculator back up. And we're going to first take the current. 84 divided by 12 equals, give that a negative, plus 21 divided by 3, I'll just call that 7. And it would be 7 negative. And 0 over 6 is going to be 0. So our current for the start is minus 14 amps. And we're going to store that. Clear. And our values, once again, 12, 1 over x, plus 6, 1 over x, plus 3, 1 over x, equals 0.583333. Take the reciprocal, times memory recall, equals 24 volts, or minus 24 volts. And if we were to go ahead and do the math and all that, like they did, we end up with, whoops, there we go, minus 24 volts. Really have to get my pin paired squared away here. So the voltage across XY is, oops, maybe that's why I had it at an angle. I never do things straight across. There we go, minus 24 volts. And that's all there is to Millman's theorem. And if you go back and look at everything we did, we found that, oops, I said up, 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 keep going. There we go. Our Thevenin voltage was, how about that, 24 volts, looking at it across any 2 points from that circuit that we were looking at earlier. So that is the ease and beauty of Millman's theorem. Now, next week, we are going to look at the analysis of delta and Y circuits, which is what we have here, T or Y, or pi, also known as delta circuits. And it's useful in analysis to be able to convert back and forth between the two, because one may have an easier analysis than another. And we'll look into that as we go through next week. Then after that, what are we going to do? I'm pretty sure that's the end of chapter 10. Delta to y. Yep. Yeah, so the delta and y circuits are the end of chapter 10, and then we'll talk a little bit about chapter 11, which is basically wire switches, stuff like that. And then chapter 12 is batteries. And once we get done, I'm not going to go heavily into batteries or the wires. I'm going to let you take care of that in your reading. So the delta to y, and then the high points of chapter 11, chapter 12, and then we're done, guys. From that, it's up to you to ask me questions to clarify anything you think you need clarification on, and I'm more than happy to do it. As usual, Wednesday night, back sitting in my office waiting for somebody to come ask me questions, and then lecture next week. So I'll see you when I see you. You guys be good, and that's about it. Bye.